Now next we will discuss about the field. In the vector space, field plays very important role. That's why we must know which set is called as field, which properties this set satisfies, and what are the elements of field. Now any non-empty set F having at least two elements with two binary composition plus and dot called as field if following axioms are satisfied. Now what does this mean? This means that field is any non-empty set whose elements under two binary composition, one is depicting addition and another depicting multiplication, satisfy certain properties is called as field. Now what are the properties under addition that elements of field must satisfy is, if we take any two elements from the set F then and apply the binary composition of addition on them, the result must be from the same set, and this property is called as closed property. Its another name is closure property. Second property is, if we take any three elements from the field F and we apply the operation on them as add A and B, then result added to element C, or add B and C first and result add to A, in both cases we get the same result, and we are familiar in mathematics with this property as associative property. Now our third property come up with the existence of additive identity. What does identity mean? Identity implies it will not lose the identity of any element. Implies if A and for every A in the field F, there exists the element 0 element in F. Here 0 depict the element of additive identity. It doesn't mean that if we are talking about F, we always have the 0. This 0 changes according to the definition of field F. If we are talking about the set of matrices, then this 0 represents the 0 matrix. If we are talking about the set of polynomials, this 0 represents the 0 polynomial. If we are talking about the reals, integers and even numbers, odd numbers set, then this 0 represents simple 0. And the property says that for every A belongs to F, there exists 0 belongs to F such that whatever we do, we add 0 from right of the element A or we add 0 from the left of the element A, it always return the same element. This property is called as existence of additive identity. Now in field F, this additive identity is always unique. This implies it cannot happen that a set is called as field and there are two elements which satisfy this property. Now next property under addition is, for every A in the field F, there exists minus of A in the field F such that A plus minus of A gives you the additive identity. Minus of A plus A gives you additive identity. This implies if we are talking about the field F, then it must have corresponding to every element exactly one element, which when attack on this element from right or from left under the composition of addition, we always get the additive identity in result. Next property is, for every A and B in field F, we have the A plus B equal to B plus A. That is, whether we add A in B or B in A, we always get the same result, and this property is called as commutative property. Now what we have is, if we are talking about the field, then under addition which properties must be satisfied? First, if we add any two elements of the field F, then we must get the element of field F. If we take any three elements of field F, then they must satisfy the property of associative law under addition. If we take any element from the field F, then corresponding to that there must be the additive identity in the field F such that whatsoever we add from left or from right, the result must be the same element. Next, existence of inverse. Corresponding to every element, there must be the inverse of that element, which when operated under the binary composition of addition, the result must be the additive identity. And all the elements of F must satisfy the commutative law under the addition property. Now next, what are the properties this must satisfy under the multiplication? Now say all the properties, that is first second properties are same, that is the group or the set to which we have to call the field must satisfy the closure property under the multiplication. That means if we take any two elements from the field F, multiply them, again we get the element of field F. Now this is not necessary that this multiplication always implies the simple multiplication. Its definition can be changed or could be changed according to the set F, or accordingly we have to make the F as a field. It will be depicted in the example in further discussion. Now next is the associative property. What does this property say? If we take the three elements from the field F, whether we multiply B and C first then multiply A, or we multiply A and B first then multiply C, in both cases we get the same result. Next is the existence of multiplicative identity. As we all know, in this case of set of reals, what is the multiplicative identity? This is unity. Multiplicative identity is also called as the unity. What this property says, that for all A in F, there exists unique element 1. Whatever we do, we multiply 1 in A from left or we multiply 1 in A from right, every time we get the same element A. And here 1 is what? This is multiplicative identity. Now keep in mind that in field, the multiplicative identity is unique. As the inverse is unique, we have the multiplicative identity is unique, and as the multiplicative identity is unique, in next property we have the inverse is unique. What this property says is, for every A in F, there exists B in F, such that whether B is operated with A under multiplication from left or from right, what we get is the multiplicative identity. Now one most important thing to keep in mind is this A is all the elements of field F except that of our additive identity. Other than additive identity, all the elements must have the inverse, so that whenever they are operated under the binary composition of multiplication, the result must be the unity. Next is commutative property. Now what is our commutative property say? That for all A and B with F, that is, if A is communicating with B, then B must communicate with A. That implies whatever we we apply multiplication in A in B or B in A, in both cases we get the same result. Next is distributive law. As we all know, the distributive law, its name itself is clarifying that something is distributed over something. Now what is that something which is distributed? Obviously these two properties, addition and multiplication. In this case, we will check whether the multiplication is distributed over the addition or not. Now in this case, we have the two properties basically, obviously. Now if we have the three elements A, B and C from the field F. Now what the distributive law says, if B and C are added and operated from left as with A under the multiplication, the result is the same as that A is multiplied by B and A is multiplied by C, and results are added. Similar is the property on the second base, and if the B and C are added and then A attack on B and C from right under multiplication operator, then the result must be same as B into A plus C into A. The first property named as left distribution. Why left distribution? Because the A is on the left and multiplication distributed over addition from the left side. And why second property is called as right distributive? Because B is on the right and multiplication is distributed over B and C from the right side. Okay, these are the properties. Any non-empty set with at least two elements. Now why we have called at least two elements? Because we need two elements compulsory. One is your identity, that is additive identity, and another is your multiplicative identity. Now there occur some set which has these element. Now we can deduct those sets immediately to be a field which has none not has at least one of these two elements. If a set doesn't have the zero element, that means obviously this is not field. If element doesn't have the multiplicative identity, it means it is not a field. That's why in the definition we have mentioned that F is any non-empty set with at least two elements. Now these at least two elements, one is additive identity and second one is multiplicative identity. Now what are the fields? For example, the set of all reals with respect to addition and multiplication defined on it is field. We know how to add the real numbers. We all have the knowledge about that. We know how to multiply the real numbers. We know in reals all the elements satisfy the closed property, associative property. The additive inverse of every element A is minus A. The additive identity is 0, simple 0 element. Commutative law holds by all the elements of reals. Next, all the reals satisfy the properties under multiplication, that is multiply any two reals, you will get the real. Associative property hold on the real whether you multiply A in B and C or you multiply AB and then C, you will get the same answer. Multiplicative identity is unity. Your multiplicative inverse of every A other than 0 is 1 by A. Commutative law holds on reals. Distributive law holds on reals. So set of reals is a field under usual addition and multiplication. Second, we come up with the example of all the matrices of 2 cross 2 order which satisfy the property A, B minus B, A. Which are these matrices? These are skew symmetric matrices of order 2. Over the set of reals implies each of A, B comes from the reals. Under usual addition and multiplication, this is again a field. Next, set of all the even integers under usual addition and multiplication is not a field. Now why it's not a field? Because in even number, as I have already said, two important elements of any field are its identities. One is an additive identity and second one is multiplicative identity. And when we call about the set of even integers, what is missing over here is multiplicative identity. As we know in integers, multiplicative identity is 1. 1 एक ऐसा एलिमेंट है जिसको a में मल्टीप्लाई करो तो you चाहे लेफ्ट से करो चाहे राइट से करो, you will always get the element a. Therefore, this set is not a field because of non-existence of multiplicative identity. Next is set of rational numbers. I have already discussed this. Addition and multiplication operations can be different according to the definition. Now what here is given you that if A and B are two elements from the set of rational numbers, then A plus B depicts A और B को add करो और 1 को subtract करो. And what does multiplication depict? It gives add A and B, subtract the multiplication of A and B from the result. This is true for all the elements of A, B in Q. Keep in mind always whatsoever is given. Here addition is defined. Add the two elements, that is add two rational numbers. Whatever answer you are getting, subtract 1 from that. And when we talk about the multiplication, then add those two elements and subtract their multiplication from that. Now we come up with this. What will be the additive identity and what will be the inverse? Because you are familiar with how to solve it. The closed is obviously it's closed because 1 itself is a rational number, a is a rational number, b is a rational number. When we add two rational numbers, we get the rational number. When we subtract two rational numbers, we get the rational number. So this will definitely satisfy the closed property. Second, come up with associative law. These are the results are rationals. Rationals are associative under addition. So it must satisfy your associative property also. Now come up with the addition. Now in this case we cannot say that the additive identity is 0. Now see what will be the additive identity. If I have 0 is the additive identity, then a plus 0 implies a plus 0 minus 1. The answer we need is a. This implies a minus 1 is a, because whenever we add the additive identity, what we need is whenever we add here 0, then result must be the a. Now how a will come up? This a will come up only when a plus 0 minus 1 is equal to a. Now this cancelled. Here 0 is 1. It doesn't mean 0 is 1. Okay, don't get confused with 0 of q. For the well-being, you can apply it with the capital 0. We have operated it as the capital 0. This is capital O. We depict the identity, additive identity as O, not as 0. Here a plus 0 implies, what is 0 in this case? Additive identity in this case is 1. That means 1 is the element of the set of rational number which when operate on a, either from the right side or from the left side, we will get the answer a. Okay, next is you want to have the inverse. Now we talk about the inverse. A plus, let's say inverse is minus of a. Don't cancel it out. This is not minus a exactly. Then the result must be additive identity. Now in this case additive identity O is 1. Now this implies what we operation say, it must be a plus minus a minus 1 is equal to 1. Now minus a, what exactly minus a depict in this case is minus a is equal to 1 plus 1 minus of a. This is equal to 2 minus a. That means in case of this set, the inverse of a must be 2 minus a. It implies 2 minus a will operate it on a from right or left. The answer will be 1. That is our additive identity. Okay. Now we will talk about the multiplicative identity. What does multiplicative operation say? A dot b is equal to a plus b minus ab. Let us suppose that multiplicative identity be 1. Then what we need, the result is a. That means a plus b, a plus 1 plus minus of a dot 1 is equal to a. Don't cancel it out. Here 1 doesn't mean the exactly 1 we were talking about. Now this implies you need here the result is a. Now this implies 1 minus a into 1 is 0. This implies 1 is a. It's not unique. Not a unique result implies matlab corresponding to each a, the additive inverse, the multiplicative inverse must be your same element. So this cannot be a field. For more elaboration, let's have a look over here is as now this is our element a. What does property say? A dot b is equal to a plus b minus ab. Let us suppose that let E be multiplicative identity. Identity of Q. What we need is a dot E must come up with a. The result say a plus E minus E into a. This is equal to a. This must be equal to a. what does property says? Whether you operate the identity from the left or from the right, you must get the result. Here we have to prove the property that whenever A is operated on E from the whenever E is operated on A from the right side, the result must be the A. Therefore, what this operation was defined as A plus E minus EA is equal to A. Now these A are same. One more thing about the multiplicative identity was that the element with which we are dealing and talking about the multiplicative identity, that must not be our additive identity. So A is not 0, where 0 is 1. Therefore A are all the elements of the field of rational set of rational numbers except that of 1. Now whenever E operated on A from the right side, answer is A. Here what does this operation implies? Whenever that it's operated on two elements, it come up with the sum of elements minus the product of elements. But we need the result as the same element. Therefore E is into 1 minus A is equal to 0. A is all but except the additive identity. Therefore A must not be 0. So whatever E come up with the 0. Now check. If we apply 0 from the left side, what we get is 0 plus A minus 0 into A. Here 0 is same as simple 0 we talk about in the number theory numbers. Then this is A. Get the answer. When 0 operated upon A from the left, it's giving the same element. When 0 operated upon A from the right, it's giving the same answer. That means what is 0? 0 in this case is 0 is multiplicative identity. Okay, don't get confused with it. We were discussing the set of rational numbers. If we are under the usual addition and usual multiplication, then undoubtedly 0 is our additive identity and 1 is our multiplicative identity. Because whenever we simply add the 0 in any element, we get the answer the same element. And when we multiply 1 in any element, we get the same element. Now where the difference occurs? Difference occurs here is on the definition of addition and multiplication. Here the definition of addition was something else and definition of multiplication was something else. What was definition of multiplication saying? That whenever we multiply two elements, what we get is sum of those elements minus the product of. What does addition says? That whenever we are operating the two elements with the binary composition of this symbol, we are getting sum of those elements minus the unity. Okay, now this is the field as it's satisfying all the properties. बाकी सारी प्रॉपर्टीज तो ऑब्वियस ही थी अंडर एडिशन मल्टीप्लिकेशन क्लोजर प्रॉपर्टी एसोसिएटिव प्रॉपर्टी. प्रॉब्लम कहाँ पे आनी थी? ओनली अंडर द आइडेंटिटीज एंड वी हैव डिफाइंड द आइडेंटिटीज. इन दिस केस मल्टीप्लिकेशन आइडेंटिटी इज 0 and additive identity is 1. Both are the rational numbers existing in the set. That means our set is field. After field, now we will come up to our main topic, that is vector space. Now what is our vector space? What does mean by vector space? Vector space, it must be some set in which elements must satisfy some of the property. Now why vector space? इतना सारा हम लोगों को डेफिनेशंस की ज़रूरत क्यों पड़ी सिर्फ इस एक स्पेस को डिफाइन करने के लिए? As its definition starts with field. Now field is composed of two binary composition. One is plus and another is multiplication. And both these composition are what? These are internal compositions. Now what this says, if F is field, V is any non-empty set with two compositions. अब दो सेट डिफाइन किए हैं तो पक्का इन दोनों सेट में कोई ना कोई रिलेशन भी डिफाइन किया होगा. एंड दैट रिलेशन इज डिपिक्टेड विद द हेल्प ऑफ external binary composition and internal binary composition. So what does definition of vector space says? Let F be a field and V be any non-empty set with two compositions. One is internal binary composition on V called as addition of vectors and is denoted by plus sign, and other is external binary composition denoted by dot sign called as scalar multiplication. Now keep in mind, in the case of vector space we deal with the two composition. One is internal binary composition that obviously happens with the elements of V itself, and another is external binary composition. This must be the composition of elements of V with the elements of F. The external composition is also called as scalar multiplication. Now why it's called as scalar multiplication? Because elements of field are always called as the scalars. Then V is called as vector space or linear space over the field F if some of the axioms are satisfied. Now obviously these axioms will be some under the internal binary composition and other will be the under external binary composition, and there must be the sum which composed of both these compositions. Now what does these properties say? Now these properties under addition properties are obvious. These must be closed, this must satisfy the associative law, there must be the existence of additive identity, there must be the existence of additive inverse, and all the elements must satisfy the commutative law. I've already discussed all these properties under the definition of field. That means अगर हमें किसी सेट को वेक्टर स्पेस प्रूव करना है तो सबसे पहले तो वेक्टर स्पेस ने अंडर एडिशन 5 अपनी प्रॉपर्टीज को सेटिस्फाई करना ही करना है. What are those properties? Those are the closed properties. Those are associative property. Means there must be the association between the elements of the set under addition. मतलब आप B और C को ऐड करके फिर A को ऐड करो या A और B को ऐड करके फिर C को ऐड करो, every time you must get the same answer. If we take any two elements from the set, we apply addition on them, then that result must be from the V itself. If we have the, for every A in the set V, there must exist unique element 0 such that 0 operate on A from the right or 0 operate on A from the left, the result must be A. Now you have cleared that mind na, that this 0 is not necessarily the 0 we were talking about in the real number system. This 0 changes with respect to your set V. In case of matrices it's 0 matrix, in case of polynomials it's 0 polynomial, in case of numbers it's simple 0. Okay, now existence of additive identity. What does additive inverse, what does it say? Corresponding to every element we must have the inverse of that element. Okay, for every A there exists minus of A such that और A right से operate हो minus A left से operate हो, what you get is additive identity. Then commutative property. Now where the change occur? Change occur here on the external binary composition, to which here we have also declared as the scalar multiplication. Why scalar multiplication? Because we are going to multiply with the elements of field F. What these properties is? Again these properties are same, we have already discussed, that is there must be the existence, there must be the closed property, there must be what we say is the associative property, there must be the distributive property, there must be the existence of unity element. Now come up with these properties. What these say? If R is element from the field F, we take the element from the vector space, we operate that the element of field attack on the element of A, what we get is the result in V. मतलब R A पे अटैक तो करता है पर फंस कहाँ जाता है? V के पास ही. Next is, this is closed under scalar multiplication. Next is, take any two elements from the field F, take the element from V, then what we get is, अगर ये दोनों भी इकट्ठे होके आ जाएं, then even क्या करते हैं? डिस्ट्रीब्यूट हो जाते हैं. R1 plus R2 into A is equal to R1 into A plus R2 into A. Third property, if we take any element from the field F and two element from the vector space, मतलब पहले क्या था? फील्ड के एलिमेंट ऐड होके आ गए तब भी डिस्ट्रीब्यूट हो गए, अकेला भी आ गया तब भी डिस्ट्रीब्यूट हो गया. Next is our associative property. Now keep in mind, whenever we are talking about the associative property under scalar multiplication, then two elements must be taken from the field F and one from the set to which we have to prove the vector space. And what the associative property says, R1 into R2 is equal to A. That is, आप दो एलिमेंट्स को मल्टीप्लाई करके फिर A में मल्टीप्लाई करो, या पहले एक एलिमेंट को A में मल्टीप्लाई करके फिर दूसरे में मल्टीप्लाई करो, every time you will get the same answer. Next is, if A is any element from the vector space V, then we have the unity in F. Now what this unity depict? This is multiplicative identity of your set F, to which we have called as field. Then the multiplicative identity of field F, when multiplied by the vectors of V, it will come up as the left identity of your vector space. What does left identity mean? That is, this identity will attack your vector from the left side. Now all the properties we have defined under the scalar multiplication as a mapping from F cross V to V. That means all the scalars are from the left side, not from the right side. Okay. Now if there is any set which satisfy all these properties, these 5 under addition and these 5 under scalar multiplication, that will be called as vector space over the field from where we have taken the scalars, and this is represented as V over F is a vector space. This is vector space. What does it mean? V is a set which form the vector space over the field F. Now for more elaboration, we will discuss a simple example for proving that this is a field. This example is, let R be a field of real numbers. I have already proved you people that the set of reals is satisfy all the properties of a field under addition multiplication. That's why it's a field. And V is set of all the vectors in a plane. Then VR, I have already proved V. What does VR means? We have to prove that V is a vector space over the set of real numbers with in addition as internal binary composition and scalar multiplication of elements of R with those of V as the external binary composition. Okay, आपको V दिया हुआ है. V is a set of all the vectors in plane. प्लेन में वेक्टर्स क्या होते हैं भी? प्लेन्स में वेक्टर आपके होते हैं ऑर्डर्ड पेयर. दैट मीन्स दीज आर द, एक एलिमेंट एक्स एक्सिस का हो गया, एक एलिमेंट आपका हो गया वाई एक्सिस का, एंड बोथ दीज एलिमेंट्स आर टेकन फ्रॉम द रियल्स. क्योंकि प्लेन की बात कर रहा है, दैट मीन्स प्लेन इम्प्लाइज द रियल नंबर सेट. सो V is any set with the ordered pair of the elements of reals number set. ठीक है. Then addition is defined and scalar is defined as, it take two elements from the V and any element from the set of reals, add the elements of V, we will get first coordinate plus first coordinate, second coordinate plus second coordinate. This is usual addition. Now what usual scalar multiplication depict? This implies scalar multiply by any vector, you will get R into A1, R into B1. Now to prove this is a vector space, we have to prove all the properties of vector space over here. What were these properties? Under addition, we have to prove that if I take two elements of vector V and add them, I get the vectors of V. And for being any vector of V, what we have to prove is the result is a ordered pair like this, first coordinate and second coordinate, and both the coordinates are the elements of reals. Second was associative property, that is whatever you are taking the three elements, add first two elements and then the third, or add the last two elements then the first, you will get the same answer. I have to find the identity over here, I have to find the additive inverse over here, I have to find the commutative law. Then under scalar multiplication, some properties, that is 5 properties, closed properties, associative and distributive, and the unity element is to be discussed. Let's start. First come up with the closure, that is closed property. What does this property says? Take two elements from V, add them. What addition depict? This comes up with the first coordinate added in the first coordinate, second coordinate added in the second coordinate. Now what about A1, A2, B1, B2? What does it means? That these are the reals, and we know if we take any two real numbers, add them, you will get the real number. That's why I have written here A1, B1, A2, B2. A1 plus A2 is a real. B1 plus B2 is a real. We have not discussed any other addition. Why? Because we need just about these two and these two. Okay. Now this is ordered pair over the field R. That's why this must be the element of V. Next is associative property. What does associative property say? Take three elements, add these three elements. First I have taken the composition of first two, then add the third element in it. This composition will come up with like this: A1 plus A2 plus A3, B1 plus B2 plus B3. Now we know that A1, A2, A3, B1, B2, B3 these are the reals. और रियल्स में क्या होता है अभी, चाहे पहले में दूसरा ऐड करके फिर तीसरा ऐड कर दो, या पहला अलग रख के दो पीछे वाले दो को ऐड करके फिर फर्स्ट वाला ऐड कर दो, यू विल गेट द सेम आंसर. वी डिस्क्लोज दिस कंपोजिशन इन अवर टर्म्स एंड गेट दैट अगर ये केस रियल्स में ट्रू है तो हमारे ऑर्डर्ड पेयर के सेट में भी ट्रू है. तो यहाँ पे क्या आ गया, हमने लिया था फर्स्ट एलिमेंट, add first two element, then add the third element. What we get is the result is same as add the last two element, then add the first element. Okay, so the associative law holds on V. Next is existence of additive identity. What additive identity required was, एक ऐसा एलिमेंट ढूंढना है हमें सेट V में जिसको V के एलिमेंट्स में चाहे लेफ्ट से ऐड करो चाहे राइट से ऐड करो, वी मस्ट हैव द रिजल्ट एज द same element. Now what we are doing is A1 B1 plus two elements is equal to A1 plus 0, B1 plus 0 is equal to A1 B1. 0 0 एक ऐसा ऑर्डर्ड पेयर हमें मिल गया जिसको A1 B1 में राइट से ऐड करो चाहे लेफ्ट से ऐड करो हमें सेम आंसर मिल गया. ओके, now we 0 0 is our additive identity. Next we come up with the additive inverse. As we know that the field is real, so हर A का जो additive inverse होता है, हर A के corresponding वो ऐसा element जिसको जब add करो तो आंसर आपका 0 आता है, that is your minus of A. Though corresponding to AB we have the minus A minus B. Reason क्या है, AB reals हैं तो minus A minus B भी real ही होंगे. AB minus A minus B, this come up with A 0 0. Then minus A minus B added in AB, you will come up with 0 0. That means corresponding to every AB inverse is minus A minus B. Additive inverse existence. Then commutative law. Take any two elements from the B as A1 B1, A2 B1. Add those two elements. What you get is this is real, this is real. I know reals are commutative. This implies A1 में A2 ऐड कर दो या A2 में A1 ऐड कर दो, कोई फ़र्क नहीं. B1 में B2 ऐड कर दो या B2 में B1 ऐड कर दो, कोई फ़र्क नहीं. That means this will be equal to A2 plus A1, B2 plus B1. So the answer come up with A2 B2 plus A1 B1. So addition is commutative over V also. Now under scalar multiplication, take one element from the field R, one element from V, multiply scalar in the ordered pair. This is RA, RB, RAB. All are reals. It implies RA, RB is also real. This implies this ordered pair is the member of V. Now take the element from R, take two elements from V, add elements of V, operate the element of R, you will get this composition R into A plus A1 plus A2, B1 plus B2. Then R operate on these from left. Otherwise these all the reals. Reals पे आपकी associative distributive law hold करता है. That means this will come up with RA1, RA2, RB1, RB2. Then separate R from these, we will get R into A1, B1, R into A2, B2. That means this composition satisfies the distributive property. Then in next property, take 2 from R, 1 from V, operate same operation, you will get the separate result. Next is the associative law. As I have already mentioned, in case of associative law, you have to take the two elements from the field and one element from the space to which we have to prove the vector space. R1 and R2 then multiplied in the ordered pair AB. What you get is R1 times R2A, R1 times R2B. Now why I have done here this kind of the separation? Because all these are the real numbers. Then separating them you will get the result. दिस वॉज टू बी प्रूव्ड ना. पहले R1 में R2 मल्टीप्लाई करके फिर वेक्टर स्पेस के एलिमेंट में मल्टीप्लाई कर दो, या फिर R2 में वेक्टर स्पेस का एलिमेंट मल्टीप्लाई करके फिर R1 में मल्टीप्लाई कर दो. यू मस्ट हैव द सेम आंसर इन बोथ द केसेस. Next, last property. This is the important property. Keep in mind, without unity we cannot prove that the set is vector space, and this unity must be the left unity. That is, there must be a unity in R, which when multiplied in our vector from the left, it gives us the same element of vector again. As we is satisfying all the 10 properties, 5 under addition, 5 under scalar multiplication, this implies this must be a vector space. Okay, we will carry on to the next session. Thank you.